Now we complete the Gaussian elimination introduction, and we also introduce a very important concept called the inverse of a matrix. Yeah, while I prefer using the definitions to talk about the inverse, but we cannot always find the inverse. Just use the definition, trying to fix the output back to the input. This is only a beginning for understanding the inverse. Because after all, we still need something we can rely on. We still need something like an algorithm to perform the process so that we can find the inverse of any matrix if there is an inverse. And there are two methods in finding the inverse of a matrix. The first one is called Gauss-Jordan method. Yeah. Clearly, this term comes from two mathematicians. Gauss is the Gaussian, which invents the Gaussian elimination, and Jordan completes the second part. So let's consider this example. 2, 4, minus 2, 1, minus 6, 7, and 1, 0, 2. We have dealt with it for several times. The beginning for Gauss-Jordan methods is to put an identity matrix following it. E1, E2, E3 here means identity vector, including 1, 0, 0, 0, 1, 0, and 0, 0, 1. So A is followed by I. The first step is a standard Gaussian elimination. It's completely the same as Gaussian elimination. So when we perform the Gaussian elimination, the result should be 1 minus 2 minus 1 here, and 0, 1, 1 here, and 0, 0, 1 here. Oh no, that's the second part. The result for Gaussian elimination is 2, 0, 0, 1 minus 8, 0, and 1 minus 2, 1. Remember, the goal is to have an upper triangular matrix where we can see pivots and the independent structure easily. That's only the first part. We call such a matrix augmented matrix or augmented form. Augmented matrix. This augmented matrix is found by the original A. When A is attacked with something, we call such something augmented matrix. So by using the straightforward Gaussian part, we lead A to U. And because we keep doing those manipulation, row operation, so let I, the augmented part, will be changed. It will be no longer I. So let's find what we get from this process. First of all, 2, 1, 1 is A, right? But we no longer deal with 2, 1, 1. We deal with 2, 1, 1, 1, 0, 0. The new first row is an augmented part. And we multiply the first row by minus 2 and add it to the second, right? So 1 times 2, minus 8. And minus 2, just like before. But the thing is, here, 1 times minus 2 and add it to the second, produce minus 2 here. Minus 2, 7, 2, 6, oh no, 0, 0, 1. So the new change is this minus 2. It makes the original I be different. Similarly, the next step, when we perform this part, we don't care about what has been changed in the augmented part. We end at A, we try to make A as U just like before. So 2, 1, 1, 1, 0, 0, 0, minus 8, minus 2, minus 2, 1, 0 are the same. But we multiply the first row by 1 and add it to the third, which makes this 0, 8, 3. And the key is this one is no longer 0. It becomes 1. So the identity matrix is also changed regarding the 0. And finally, the last step, 2, 1, 1, 1, 0, 0. 0 minus a minus 2 minus 2, 1, 0. And we multiply the second row by 1 and add it to the third. So 0 and the key 0, 1. So a becomes u. Theoretically, Gaussian elimination stopped. But for the augmented part, there is still something to do. It's the second row by 1, multiply the second row by 1 and add it to the third. This is why we have 1, 0, 0, minus 2, 1, 0, and minus 1, 1 for the augmented part. No longer an I. And the structure is like a lower triangular matrix. Yes, and this is not surprising because originally we start by A attacked with I. This is the initial state. And what is done in Gaussian elimination? L inverse. We keep performing row manipulation, which is reported in L inverse, right? So L inverse make A be an upper triangular one, and L inverse also make that I be L inverse here. So this also produce a shortcut regarding L inverse. L inverse is attracted because L inverse make A into U. So if we would like to find L inverse directly, what can be done? It can be done by an augmented matrix I, A and I together. And when you perform standard Gaussian elimination, the L inverse will appear in that augmented part. The I will be L inverse. Okay, but this is nothing new. It's just a fancy way to find L inverse. Actually, an easier way. But even we find L inverse, the goal is to determine A inverse, not L inverse. So how do we get the A inverse? This is where Jordan comes in. Jordan concerns the second part, the second step. So let's start by this augmented matrix, U and L inverse. The process of the second part is to do whatever you can. Make the first U be I. Just keep performing row operations. Multiply some rows by something and add it to another something. Make this U be I. That's the key. So let's do it. Let's do it here. So this is unlike the forward part. We start by the third row and do it backward. We have to multiply the third row by 2 so that we can make this coefficient 0. Let's make it 0. But the way to make it 0 also makes other entries change. We multiply the third row by 2 and add it to the second, right? So it is 0, negative A here because there's nothing you can do for 0 and 0 in U. But this minus 1, change the entry here. When minus 1 is multiplied by 2 and added to these entries, it becomes minus 4. Similarly, this 1 is no longer 1, it's 3. And this one is 2 based on your operation. So the first step is to make the second row to have a 0 sitting on 1. We are going to make it be I gradually. So the next step is to make this entry be also 0. This makes the column here a bit like 0, 0, 1, the unit vector. So how do we make it 0? We have to multiply the third row by -1 and add it to the first, right? So this makes 1 for this and 2 for this. But when you multiply the third row by 1 and add it to this one, it produces 0. Yeah, it produces 2. I beg your pardon. It should be 2 here, because minus 1 multiplied by -1 and added to the first be 0. Similarly, -1 times -1 is 1, and 1 add 1 gives 2. So it is 1 here and -1 here. Yeah, this should be -1 because I multiply 1 by -1 and add it to the first. Okay, so how about the next step? Remember, what we keep doing is to generate an identity matrix for U. So what has been achieved doesn't need to be changed, but I have to divide the second row by -8 so that I can produce 0, 1, 0, which is more like an identity matrix. But here it will be 1 over 2 and -3 over 8 and -1 over 4. With this at hand, this is already 1, right? So we multiply the second row by -1 and add it to the first, which will give 2, 0, 0, 3 over 2, -5 over 8, and -3 over 4. Yeah, almost there if we divide the first row by 2. So 1, 0, 0, 3 over 2, no, 3 over 4, and -5 over 16, and -3 over 8. 0, 1, 0, 1/2, -3 over 8, -1 over 4, and 0, 0, 1, -1, 1, 1. So finally, we make you an identity matrix, and that ultimate goal, A inverse, will be shown here. Yeah, this is the A inverse. This is called Gauss-Jordan method to find the inverse of A. But why? Why A inverse will be there? The first part is the standard Gaussian elimination, and the second part is like a backward elimination, which doesn't generate only lower or upper triangular matrix. It makes an originally upper triangular matrix be an identity matrix. But why an identity matrix there leads an A inverse to that position? Why there is an A inverse? So the original process for A and I is L inverse, right? L inverse make U and the L inverse as an attack part, which was originally I. And what we keep doing, let's make U be I, should be U inverse. Yeah, because U inverse gives U to I. U inverse will transform U to nothing happen. So it is U inverse that we keep doing in the second part. We don't know what we are doing in the beginning, but when U is turned into I gradually, all those row manipulation is U inverse. So it is U inverse. Here, U inverse make U L inverse to I, and U inverse will also make the following L inverse be U inverse L inverse. right? So what does U inverse L inverse mean? Yeah, A equals LU, and the inverse of A would be the inverse of LU, and due to the nature for matrix manipulation, LU inverse will be U inverse and L inverse. So it is U inverse and L inverse that appears in the end, and U inverse L inverse happens to be A inverse. So this is why that we generate A inverse here. If you keep making the forward part I, it will also make the attack part A inverse. Yeah, so this is the first method in finding the inverse of a matrix, Gauss-Jordan matrix. So we can see the A inverse just based on this process. And finally, the last remark in the first section is we can combine the inverse of A and the non-singular A together. Initially, we talk about independent or dependent for vector, which becomes non-singular or singular for a matrix. Then we talk about the inverse of a process. They should belong to two different stuffs. Non-singular or singular concerns independent or dependent for vectors. And the inverse or not is another thing. But in the process of Gauss-Jordan method, as you can see, if a matrix has n pivots, it's called a non-singular matrix. And if a matrix is singular, you cannot have 4 pivots. The number of pivots must be less than its size. But if you have a 0 in that pivot position, which is no longer a pivot, I know, but that must break down the Gauss-Jordan process, because you can never get an I or L inverse in that process. The first half is to get an L inverse in the attack part, and the second half is to have an U, is to keep performing U inverse and get an I in the first part. In either part, once there is no more pivots, you can never generate an I in the second half or L inverse in the first half. This breaks down the Gauss-Jordan method. So we can connect the two conditions together. If a matrix is non-singular, there must be an inverse. In contrast, if a matrix is singular, you can never find an inverse. Inverse and singular are just like one side of each other. We can connect them together. So my final remark here, if a square matrix is invertible, then it must be non-singular. And this is a dual directional statement. If a matrix is non-singular, there must be an inverse. So with this understanding, we can move to more formal language in linear algebra, vector space. Initially, we talk about entries, and then we understand that columns could tell more. Yeah, by identifying columns, we can put them together, and the AX becomes the linear combination for all the columns. However, at this stage, if you have a matrix 2 by 3 like this, yeah, you can read this as first column, second column, third column. We can read those columns one by one, 2, 0, 1, 0, 4, 3. The education here is to make you know there are more columns behind it. You see A as the combination of 3 columns. Actually, it is not. A is just a sample from something bigger. It has a bigger picture for this column. You see 3 columns, but you have the whole space or subspace. But this cannot be done by some definition for space or subspace. So we start by something you already knew. If you have an xy plane, you already know that it's an R2 plane. The dimension is R2, where 2 means the number of entries. Like 3, 4, a vector in xy plane, 5 minus 2. We count the number of entries and say each vector is from R2. This is just the trivial way, and this is nothing wrong. Yeah, it's trivial, but it is correct. Yeah. Actually, when vectors are sampled from a space, that space must satisfy the A rules shown in this slide. Commutativity, associativity, additive identity, existence of something, blah, blah, blah. But this is not important at all. The A rules are not emphasized in any kind of scenario because we care more about subspace rather than space. Just by reading this term, literally, subspace is a subset of space. Yeah, this subs is like a subset. But it is more than just a subset. An example is R2. If you have an R2, X1 and X2, there are a lot of subsets in this R2, like a dot, a point. This point is a subset in R2. It is R0, right? So R0 should be a subset in an R2 space. This line, x-axis, x1 axis, is also a subset. The second quadrant is also a subset. Yeah. This half plane, the negative half plane regarding x1, is also a subset. All of these are subsets, but only few can be called a subspace. Because if vectors form a subspace inside a space, which is more than a subset, they have to fulfill the two definitions here. The first definition is that x and y are in the subspace, then x plus y must also be in the subspace, additive property. And the second one is if x is in the subspace, then cx must be also in the subspace, the homogeneous property, in other words. So if you have learned some linear system or even circuit theory, the two conditions can be combined as superposition. It means if x and y are in the subspace, then their linear combination must also be in the subspace because they must fulfill the additive property and the homogeneous property. But we don't have to bother the term additive property or homogeneous property here. Yeah. The thing is, let's observe the second property. The second property already ruled out a lot of subset. For example, the beginning one. This dot, the point here, is a subset, but it is not a subspace because once you multiply this by any number like 3, it will be moved here. So it cannot be a subspace because it violates the homogeneous property. So if a point is multiplied by something and it must stay there, it cannot be changed. Yeah, the only thing that fulfills this condition is origin. So yes, the origin is the smallest subspace of every space. It's of course a subset, but is also a subspace for every space, as when you cannot trace the origin. You multiply 0 by any scalar, it stays 0. And this also means that the second quadrant is not a subspace, because if you multiply this by a negative number, for example, let's consider minus 3, 4. If you multiply this by minus 2, then it will be shift to the fourth quadrant, which is out of the original subset. It's no longer in the second quadrant. So this means that the second quadrant cannot be a subspace. So once a subset be a subspace, then we must have we must have includes the origin, and we must satisfy the additive property. So for example, if I just plot an arbitrary straight line which does not pass through the origin, this can never be a subspace. Once a subset does not include the origin, it can never be subspace, because if you multiply this by a certain number, it would, an example is I just simple one, and this will violate the homogeneous property. So let's consider some examples here. Now the first quadrant is not a subspace, we already know that. A line passing through the origin is a subspace, because a simplified scenario is two-dimensional plane. This line passes through the origin. So when you multiply this by a number or a plus b, the result stays there. It's a subspace. A plane passing through the origin is also a subspace. Surprisingly, lower triangular matrix is also a subspace, because once you add up two lower triangular matrices, can it be something else? Can it be an upper triangular matrix, or can it be a non-zero terms on the upper left? Never, right? 0 add 0 is always 0. The linear combination of 0 is always 0. So lower triangular matrix is also a subspace. Symmetric matrix will be a subspace too. Okay, so we are gradually moving to the four fundamental subspace of a matrix. There are just too many subspaces in a matrix. Only 4 are our concerns. Why there could be more subspaces than 4? Because if you sample just one column, this 101 is a three-dimensional vector in three-dimensional space, and this vector passes through the origin. So 101 is of course a subspace. But how about 101, 212 formed as a plane? If you span them, if you make 101 and 212 using a parallel pipe and make it as a subspace, yes, this is a plane, and the plane still passes through the origin, so it's still a subspace. There are just too many subspaces in A, and if you transpose this, this row becomes a vector. So each vector is still a subspace, a one-dimensional subspace. There are simply just so many subspaces in A. We care about only 4: column space, row space, null space, and lemma space. We are going to learn some formal languages to describe them. And of course, we need to know how to find them one by one, how to find a column space, how to find a row space, a null space, and a lemma space. With these subspaces investigated, we can know whether A is singular, even for a rectangular case. Yeah, for a rectangular A, we won't call it singular matrix. Those terms are limited to square case. But understanding this can help us to know whether a solution exists in Ax equal B. Does this solution be unique? Is this a unique solution? Does a solution exist? And what if there is no solution? So with these terms considered, let's move to the existence and uniqueness of solutions. So the goal of this section is to check a linear system, Ax equal B, and we'd like to know, is there a solution? Is the solution unique? We make that the linear equations be A. Yeah. So this is a 3 by 4 matrix, a 3 by 4. When Ax be B, three equations, four unknowns. There could be solution in most of the cases because there are less constraints than the number of unknown. It's like we have a degree of freedom to select a variable first. If you select a variable, you reduce it into a 3 by 3. So we have we can solve it using some elimination approach. This is only from high school education. It's not true. Yeah, you don't necessarily have a degree of freedom in selecting a variable. Yeah, the formal way to investigate it is through current space and null space. So let's consider another scenario. It's formed by three equations and two unknowns. So usually, when a constraint is more than the number of unknowns, we don't have a solution. So can the two columns fill out the whole R3? No, because 152 and 044 are clearly independent vectors and they can fill only the R2 subspace. I mean, each of them has three entries. So 152 and 044 must be from R3 space. But the linear combination for 152 and 044 is only R2. They cannot fill out the whole R3. So if they are from R2, I mean the subspace is from R2. Yeah. The dimension is truly R2? Or do we have a more formal way to determine the dimension? And in this way, is Ax equals B always solvable or always unsolvable? We need the concept of current space to answer it. The definition of current space is the set of all the combinations for the currents in A. We call this C parenthesis A or R parenthesis A. Yeah, it's weird because I just told you there are four subspaces called current space, growth space, null space, and lamp space. So we already have something called row space, yet R parenthesis A is not for row space. R parenthesis A is also for current space because current space is also known as range of A. So we use that letter R to call current space of A. To check whether a solution exists, we have to figure out the structure of the current space of A. And Ax equals B is solvable only when B is lie on the current space of A. And the reason is, if you consider this as a linear combination for currents, then x1 times 152 plus x2 times 044 gives B1, B2, and B3, which means that if B1, B2, B3 is not a linear combination of 152 and 044, it's hopeless to get a solution for x1 and x2. So the first thing that this system produces a solution is B1, B2, B3 must be the linear combination for 152 and 044. You cannot tell this easily by the row structure. If you use the row point of view, like x1 plus 0x2 equals b1, 5x1 plus 4x2 equals b2, 2x1 plus 4x2 equals b3, then we have to figure out whether they have a solution, because each of them is a line in two-dimensional plane. So you have to plot one x1 plus 0x2 and so forth, and to check, do I have an intercept? Do I have an intersection? But with the help of columns, it's easier. B1, B2, B3 must be the linear combination of 152 and 044. This also means that 152 must be on the column space of A. Because the definition for column space is the linear combination for all the columns. So we had advanced our knowledge. Now we know that to have a solution, the right-hand side is of course matter. But the way that right-hand side matter is, it must be on the column space of A. While you see two columns, you have more column vectors, because these columns are just samples from the column space, and the column space is denoted by x1 times the first column plus x2 times the column. For example, is 196 also a vector in the column space? Yes, because 196 is from 1 times the first column plus 1 times the second column. So I do have more column vectors by just the linear combination. So I have two columns in A, yet I have more. That's the definition for column space. And the second one is the null space of A. The null space of A is defined in a different approach. The column space is defined by the linear combination of vectors, but the null space of A is defined by a constraint. The null space of A means the X, it concerns X, that makes AX be 0. The X that can make AX be 0 is called the null space. This further tells us the number of entries for vectors in null space and that in column space is already different. Because if A is n by n, like the case here, columns are sample from Rm. R3, in this case, you can count the number of entries. So yeah, the column is sample from R3. But the X that makes AX equals 0 is from R2. It's like the X1 and X2 in this case. It's just the right-hand side is 0. When we define the null space of A, it is the X that makes AX equals 0. So R2 in this case, and Rn in general, the null space X come from Rn, and the column space vector is from Rm. We call the null space n parentheses A is also known as the kernel. Null space is a vector subspace, of course. And AX equals 0 is also called homogeneous equation. The dimension for null space is known as nullity. We'll explain this later. So for that A, do we have X that makes AX equals 0? When the right-hand side is limited to 0, And our goal is to find the null space vector. Can we find one? We can always find one. 0 is always our solution. We call this trivial solution. It means it doesn't need brain work. Everyone can figure out a solution to make 0 for the right hand side. Yeah, if you simply selecting 0, you can have a 0. But of course, trivial solutions are not our interest. We would like to find more. We would like to find those non-zero ones. So, can we find the second one? Can we find one other than 0, a non-zero solution in this case? You try hard to find a non-zero one. You would like to get x1 times the first column plus x2 times the second column and get 0. But you can never do that because this is the only way you can have 0 for such an A. It means the null space is just one point, 0, 0, the origin. This further tells us there is always null space for any matrix because you can always find the origin serving as the null space vector. It's just a point, I know, but it's also a null space vector, a point in this case. But if we select 152, 044, and 196, which obviously come from the sum of the previous two vector, and in this case, yeah, that 196 can be found by 1 plus the first vector plus 1 times the second vector. So I have a non-zero, guys. 1, 1, minus 1. In a null space, if you select 1, 1, minus 1, so 1 times the first plus 1 times the second plus minus 1 times the third will also give 0, 0, 0. So finally, we find a non-trivial solution for B. Do we have only one vector in null space? Or do we have more? Can we find the second null space solution? How about 2, 2, minus 2? If we simply multiply the first vector by any scalar, that would also be the null space solution. So you not only have the second solution, you have infinite numbers of solutions in the null space because the null space is all the point that along this vector c times 1, 1, minus 1 would be your null space solution. And 1, 1, minus 1 is a vector. It's a vector in R3. So this further tells us the dimension of the null space is R1. It's a line passing through the origin in a R3 plane. So we already knew the difference between subspace and space. 1, 1, minus 1 is a vector sample from R3. This vector is R1. So a bigger space can be found by counting the number of entries. But how about a subspace? How do we know the dimension of a subspace so far? Actually, we don't. We just figure out that if I have one vector in the null space and this vector forms a line, so the null space should be R1. It's not an official way, not yet. We can determine the dimension of a subspace once we know a very important term, basis. But they will be done later. So at least now we can express the null space in a compact way. The null space can be expressed as a scalar times 1, 1, minus 1. So let's check how to find this null space.